So, hi, I'm really happy to be here. I'm Arkouli, and indeed I'm coming from Greece, from Patras. So today I will discuss a bit widely about our work, because mainly we want to introduce ourselves here, and then given the request of Professor Zeng, I will present a paper about degradation. So, the overall title that could cover this is Implementing Digital Twins and Artificial Intelligence in Manufacturing Towards Resilient and Flexible Production. So, let's see. We'll start with the overview of LMS, who we are, where we are, etc. We will explore the importance of AI for manufacturing. So, why is this big trend important for the sector? And where it can be useful, but just a short bit. And then we will outline the key research problem and motivation for involving digital twins in predictive maintenance. And we will discuss more in the next slides. So you can see here the map. This is Greece. And in the arrow, we are pointing to Patras. This is where we are. So the Laboratory of Manufacturing Systems and Automation is part of the University of Patras, and in particular the Department of Mechanical Engineering and Aeronautics. We are very active in European-funded projects, but also national or one-to-one. And we're organized in 3 groups. One of them is the Manufacturing Process Modeling and Energy Efficiency. So they are more focused on the low level, we could say, how we can improve energy optimization in advanced manufacturing processes, how we can better model processes, etc. Then we specialize in robots, automation, and virtual reality for manufacturing. And there's also one more group, which is about integrating all these technologies in the manufacturing production from the top level. So it's about scheduling, production planning, and we will see more in a while. So I come from the Robots, Automation, and Virtual Reality in Manufacturing group. You have indicatively there some pictures from some projects that we have. And what we're doing is implementing cooperating robots to automate processes. We're also working on human-robot collaboration. So some processes that are currently manual, we see benefits in involving robots, but also they are too flexible, they are too uncertain to be fully automated. So we are also exploring the hybrid production. And of course, we have other tools to support humans adapt to the new era. So we have augmented reality, virtual reality to support upskilling and reskilling. So what is the view of our laboratory for AI? We have matched it to our 3 groups, and we face it in a hierarchical way. So there is the bottom level, where we have the processes, it's the machine, we are trying to optimize the process. Then it's a workstation, where we're trying to optimize and better plan the collaboration of resources. And then we have the complete plan. So every level needs decision making. So due to the increasing complexity of machines, systems, processes, value chains, supply chains, we need something more than the traditional tools to make decisions. So this is why we need AI. We need AI to predict the demand, so to plan our logistics. We need AI to enhance what the robots can perceive. And pretty much this is how we see it. I didn't want to take a lot of time for that, but we have 2 major groups, 2 major works that reflect our work as a laboratory. So this is a book, A Perspective on Artificial Intelligence in Manufacturing. Here we provide insights into how AI can transform manufacturing. For instance, how we can implement cooperating robots in different use cases, what's the value of predictive maintenance, real-time decision-making, and of course this is accompanied by practical case studies. But we include the human-centric approach and ergonomics, and then we conclude with strategic recommendations for integrating AI into the industrial workflows. And then we have a second work. This is from a micro level. This is a micro level approach, we could say. Here, this is an effort of the Artificial Intelligence in Manufacturing Network, the AIMNet. We are more than 17 organizations, but this work was last year when we were 17. So we provide an analysis of the adoption trends in manufacturing, the challenges, strategic goals, and the policy level, let's say. We have a discussion on the cross-cutting challenges and what are the barriers preventing wide adoption of AI. We have some KPIs where we can assess the performance of AI, and then we provide a roadmap for future AI in manufacturing policy, research, and practice. So now let's focus on the symposium subject. What is the importance of AI and digital twins in manufacturing in terms of maintenance? Maintenance is one of the key areas where we see costs. They can even reach 40% of the costs if we're not very careful with that. So we need a way to plan better the scheduling part. We need to adapt to the fluctuating demand. We need to be flexible because now we have low volume, high mix production. So we need to be informed when we plan maintenance. So, for instance, we can group the maintenance of several machines and have only one small period of downtime for the plant. An important notion here is the remaining useful life. So it's critical from the different approaches that are typically low level to predict how the complete system will react, and then to plan how to train staff, to manage the logistics of the spare parts that are needed, to avoid doing maintenance or having some defect when we have high demand, etc. So, how are we doing currently predictive maintenance, which is a framework that can allow doing what I described? There are four main approaches. So we can either go with a physics-based approach where we model the physical laws that affect the deterioration of performance of our equipment. We can either model our knowledge and then use some rules to do it, or we can use the modern AI, so the data-driven approaches. When to choose what? So, of course, each approach has its benefits. The key point is that for now we are lacking data. So a clearly data-driven approach is not only complex to implement, it also lacks data. Typically, data are not useful enough because they have noise, maybe they can be adjusted in some law. We need more thinking about it, especially if there is a complex system like a complete plant. Here we can explore the advantages of digital twins. which we see as a tool to combine the benefits of physics-based models, but also the data-driven approaches. So a digital twin is a surrogate of the machine, we could say, in the software world. It usually has three entities. We have a lot of definitions, but let's stick to the basics. It has three components: the physical entity, so the actual machine, the digital entity, and of course, flows of data and information. In our case, we can get data from the production, and then the information that we give back is when to plan maintenance. And of course, we will do that by predicting the rule of each machine and then combine when it's the exact right period to do maintenance. Here we see the approach from a paper where we tried to integrate degradation profiles into physics-based models. So why we did that? Let's say we have a model of a robot. We can see it moving in the simulation, and we can have loads, we can have whatever we want. But what happens if we run it several times? We will get the same result because simulations are deterministic. And we were looking for a way to make this change to be dependent on time. We needed to model aging. So we thought that, okay, there are several works where people are modeling degradation, but maybe for low-level parts, like not for the complete robot, but for the bearings, for the gears. So we thought of a way to integrate that in the model. To do it, we defined the framework starting from the digital model to then the prediction of the remaining useful life. So the first step, we have 4 steps. Let's move to the first one. It replies to what I need to model. How detailed should my model be? And here again, of course, we can make very detailed models or very abstract ones. The thing is that we need to balance between the accuracy that we need and the computational power that we have, but also the available information that we have. So here I have a very detailed paper about the approach, but we'll stick to the basics. Let's say we start with the kinematic and structural model of the robot and its dynamic behavior. We can then, sorry, I have asthma and something is triggering it. So anyway, then we can try and break down from the complete robot to the gearing box, gears, bearings, to the level needed. For this work, even though it's the main reason, we have not examined power supply issues and electronics, but we stick to the mechanical part. And we used 3 levels of abstraction, so the black box, gray box, and white box, to get rid of the issue what to model and to what level. So the black box is for something that we need. For instance, we need power, but we don't need to analyze it. Gray box is something that is in between. So I have some experience that can get me through. I can understand what happens, but I don't need to have the exact law that defines the working of the component, and then it's white box, which is the more analytic. This simulation has also some virtual sensors, so I can take some metrics so that I then know if something is on or not. So I can measure torques, and then we define some parameters which will allow us to adjust the behavior of the simulation model to what happens in reality. And then even simulate what will happen after the robot will work for a lot of time. So the next step is to select how to introduce the gradation. First of all, we need to identify what are the prone components for breaking down. Typically, we see gears, we see bearings, and I guess we all know wearing, pitting, cracking, all of what can happen in these two components. So maintenance records, literature data, and the manuals where people suggest how often to do maintenance. These are indicators to select what to model. Then we have to get deeper into that and try to identify the degradation processes. So how is this component deteriorating? So again, we can take more data by the same resources, and then we come to the stage where we need to assess what is there in the literature, what I can use, what I need to create myself with experiments, and how I can proceed. So we can either use some data from the literature. Typically, we see a lot of accelerated tests that can be useful, and we can even set up something ourselves. But in any case, what we should seek for is to match our parameters with the degradation curve, either one-to-one, which is the ideal case, or through a law, like a friction law. After we make this analysis, we can select some degradation curves who will allow us to adjust the model and imitate aging. Here is the mapping of the degradation curves to the modeling parameters. So here is the stage where we integrate the curves, and how we integrate them. Okay, there is a table. So we have either data or we have some formula to produce data. So what we have in our hands is matrices. So we have some parameter and we want this parameter to get values from the matrices. So in the second step, we have this thing where we exploit the digital twin to understand the status of the machine now. So in step 2, we identify how is our machine behaving. Is it brand new? Is it a bit worked? Or is it very old and ready to break down? And how we do it, we have the degradation curve, we have the behavior of the machine in the vertical axis, and we have time in the horizontal axis. So based on the values that we see in the y-axis, we match with the equivalent time of working of the machine. And then, to make the step forward and estimate the remaining useful life, we need to see how much time we have until we reach the value of breakdown. So we also need to have some thresholds for our values that signify damage. So what we're doing is, first of all, in step 2, we find where we are in y direction, and then we say, oh, I am, let's say, in the first year, I need to know what will happen in 5 years. So we go back through interpolation. So here we have the final step. We have the center, the heart, the simulation. We provide the production plan, so the loading of the machine for the time that we are interested. The question is, I will be using my machine for the next year. Will it break? So we provide the production plan for this year, or the period where we know the production plan. We provide the prediction horizon. So I need to check what will happen every week, every month, every 20 days. And then we start simulating. So we also get the current state of the machine from the digital twin, so the current value for our parameters, and then we are trying to estimate what will happen by iteratively running the simulation. And you see, we need also to define what failure is for us. Is it that the machine will have reduced accuracy, or is it that the machine will break down? We need to clearly define it, and this is a difficult question actually. First of all, if we need the machine to break down, we have no data, at least from the industry. We have to do experiments ourselves. But yeah, this depends on the researcher. That's just a framework that we propose. And let's see how we implemented it. Okay, such a framework, we need a modular way to do it, otherwise everyone will ignore it. So we try to stick with a way to minimize modeling, use ready-to-use functions, adjustability of models. So if we have robot A, B, or C, it should be pretty much the same, and then an automated procedure to make our calculations. So we selected Python that acts as the central interface for coordinating OpenModelica, where we simulate the dynamic behavior of the robot, and MATLAB, where we make the data processing and estimation part. So we use the Python 3.6, and we can see that OpenModelica supports the simulation of several machines or systems. It has a library where we can use either components or machines. So it's something scalable that we can adjust to our case. And it's integrated with Python, which is very important because we can trigger it by script and make a lot of experiments without using the software API. That's time consuming. It's open source. And then we have MATLAB, which is very easy to use for engineers. It has ready-to-use signal processing functions. It's robust. And of course, it's also integrated with Python. Where we tested it, this case study focused on implementing predictive maintenance in the production line of the inner solar tank of a thermosiphon water heater. So there's a robot that was making welds all day, and we needed to know if it will break or not. So this was in the context of a Horizon 2020 project. It was called Programs. So the aim was to estimate the point at which the welding robot will begin to underperform and it will lose the accuracy, if this would happen inside project, which it didn't. Anyway, this is how we modeled the robot. Sorry. Yeah. So the robot has 6 axes. We modeled its axis with a set of OpenModelica components. Some of them we needed to be very analytic, so they are white box, like the mechanical structure. Some of them we wanted to have analytically, but we didn't really have a lot of knowledge, so we made them gray box. And then there were some components needed for the operation, but not necessarily important for the analysis. So the actuator and the input signals were black boxes. Here is the most important part, how we selected the degradation curves. After an extensive research in what to do, we used an accelerated test from literature. You can see there it's from PM Khan. They had a ball on a disc device, and they simulated the operation of rolling bearings. We focused on the rolling bearings, and then we adjusted this, we extrapolated this for what will happen if we wouldn't have an accelerated test. And we did it using the manuals and actually analogies, okay? So we saw first of all that the gears and bearings are the parts that are highly susceptible to fail, primarily due to friction. Then we tried to see the friction's role, how it affects the robot motion. We saw that the lubricant condition is critical, and in this case study, we didn't want to accelerate tests with overloading. We needed to see what happens if we leave the robot working as is. So this is why we used the accelerated test and then adjusted for the normal case. And then here some things to mention. For the grease degradation, we usually see that it happens due to mechanical or chemical degradation, which of course is too low level if we are studying a robot. So we didn't focus on that. Then here is the plot that we saw before. Here we wanted from this curve that is the adjusted one based on the accelerated test results. We wanted to see what happens. So we started with the purple line. It was the current status. And we wanted to see what happens, let's say, in the future value, the yellow one. Here we assumed that the lubrication film thickness deteriorates and it causes contact of metals. And then we checked what happens by monitoring the torque of the different axes. So the parameter that we used as a threshold were the torques from the different gearboxes. Here is the concept, how we used the digital twin to monitor the current state. We have the robot, the actual robot, where we measure the torques. We wanted to use integrated sensors, so sensors that the robot already has. We didn't mount any additional part because this is not what the industry wants. They want to keep things as simple as possible. So we tried to see what can be done with that. And then we had the simulation from OpenModelica. Both of them had torque signals, which we compared in order to check if we are modeling the current status or something has changed. Okay. If something has changed, we change the parameters to have the simulation behaving as the actual robot. And here is what we did for the remaining useful life calculation. We had the forecasting for 28 months because this was the time left in the project, and we checked a time horizon of 20 days. The failure criteria was to see a torque deviation more than 7% in the different axes, and this was experience defined. because we expected that such a torque would cause the robot to underperform and lose accuracy in the position of the welding. So you see we have the degraded parameters, we have the future production plan, we insert them in the form of parameter values in Open Modelica, then we predict some torques, and we see, do we have the error reached or not? The error is the 7% torque deviation. So if we do, we say, oh, the machine breaks in X times, so this is the rule. If it's not, we continue doing again and again simulations until we reach the maximum time that we are interested to investigate, or some rule is estimated. And then the nominal values, where we start from, we get it from the robot controller in the first experiment. This is a picture of the results. The parameter that we modeled for the degradation, it's the friction coefficient. We did it for all the bearings. Again, I am reminding that we assumed metal-metal contact, so no lubricant. And we see how the parameters should change in time and what's the effect in the torque signal. So we estimated for month 1, 6, 12, and then it's month 18. And we compared and see we didn't find any defects. Of course, we expected that because there was another project that we had simultaneously. We ran the robot like with no lubrication, with load, etc. It didn't deviate either. The robots have, I think, around 20 years lifespan, between 10 and 20 years. So yeah, they needed something more active to see some defect. And that's actually what's challenging in industry. We want to see and predict how the machines will break, but it's not really easy. It's not really easy to find data. We need a lot of work to think how to make experiments to make machines break, but machines are expensive, so who wants to break them? So this actually is a very useful approach because it starts bottom up. So maybe we can work with the different gearboxes and then synthesize how the robot will work at the end. But of course, it would need a dedicated accelerated test bed and maybe some years on it, but on the accelerated test. So here is a close view of the previous curve. The friction coefficients, they increased steadily, which is expected because of the curve that you saw. And yeah, we ran this for 27 iterations per time. And we didn't reach this deviation. So again, this is an innovative work and we see merit in that because we can start bottom up, which is very important where we are discussing about industrial equipment. It provides insights into how degradation behavior can be used with digital twins. Of course, there are limitations, which I have highlighted. We focus solely on the gearbox also, but of course a robot, it's a complex machine. It has electronics as well. And we wanted to see what happens under normal conditions. We assumed deterministic degradation with fixed rates, and what we changed, it's maybe that different components will be at different states because they are loaded differently. But our approach, if we had the same load in all of the gearboxes, it would provide the same result. So this is something that we would like to change in the future. Of course, we need to validate this with a robot that will break. So for future directions, we see merit in combined physics-based approach with data-driven approaches and AI. Maybe now with generative AI, we can maybe imagine some defects, and with synthetic data, we can work on that. And maybe what we have now as a gap, it can be covered. And of course, we need to define confidence intervals for these degradation predictions. Okay, now I would like to introduce you to a super important project that we have. It's the flagship of AI in Europe. It's a 60 million program. We are here with all these partners from 8 countries. This project is coordinated by CEA, and its purpose is to test and experiment with AI in manufacturing. So this is an initiative under the Digital Europe program. And we are 24 partners, okay? We come from France, Germany, the Netherlands, Denmark, Spain, France. France 2 times, because it's important. Czech Republic, Greece, Spain, Italy. So what we are doing is we are creating a network of infrastructure, digital and physical, so that people, either technical providers or end user, they can come to us, and then together we can check how AI can benefit them. So we need to support AI uptake in the European market, and we develop strong reference testing and validation protocols. We also support other aspects such as trustworthy AI and the compliance with regulation. But what we do mainly is providing services, either study or testing or experimentation. These are services that correspond to different types of SMEs. So the target group is SMEs that are working either to provide solutions based on AI to the manufacturing industry, or we can have maybe end users that are looking how to improve their processes with AI. We cover all these types and maybe even large enterprises if it's necessary. But yes, we expect that this project will show what can be done with AI. It will finish in 2027. Thank you for your attention.
Thank you very much. So I think we still have some time for questions, right? So let me check who's still in the room. Do you have some questions? Yeah.
Thank you for the presentation. You gave an answer partially to my question in your conclusion perspective, but my question was precisely on introducing uncertainty and randomness in the regulation. So how do you think you are going to do this, using which kind of tools or model?
That's why we have AI in the discussion. We hope to combine AI with our model to manage uncertainty. Maybe to fake it, like maybe with some generative AI model, we can improve how random the values are in our parameters. We can imitate some defects. But the question is actually, with uncertainty.
I did not only uncertainty, but randomness as well, because some of the events, like failure of regulation, are not only uncertain, but sometimes
For example, you have a drunk worker, you know, and then destroy your machine. Or, yeah. But I think
but it's
It's a big work, yeah.
but
It's
the
a
thing is
big
that Christopher, Anne, and myself in general, actually we are quite strong on this, right? So I think the idea is if you want to consider uncertainty, we can collaborate. To start.
Sure.
Is that your intention? Okay. But actually, on the because I was developing a testing, let's say some accelerated live testing on the robot as well, on the motor level. So, but I did it in China. So actually, I had a testing devices in Beihang University, and then the idea is actually we do some kind of testing, collect some accelerated testing data to like estimate the degradation process, and then inject back to the robot. So I think that could partly answer your question. Your worry about the lifetime of the robot is too long, right? If we manage to do that. Okay.
It depends every time on the scope of the research and the available means. So it's nice to collaborate because maybe some fits better on the research of a researcher or something better on the research of another one.
Yes.
And that's the merit in collaboration.
And do you have some other questions? Or maybe from Anne, yeah.
In your example of case study with talk,
Mhm.
you consider talk as a criterion of failure. And it seems to work well. And then I was wondering, compared to what you presented with this.
Yes, the problem is with our little robot, we don't have feedback on talk. So it's a very cheap robot with no talk feedback.
Okay, so but then your point is to have another criterion for failure, which is
What is the control accuracy basically?
But more open loop.
It's still closed loop, but it's just that we are controlling the position of the gripper.
But then is there here a fund to choose a criteria for failure, depending on what is available? Okay.
Yeah.
And then the difficulty behind is not the same.
Yeah.
Kind of.
Yes. Yeah. Okay. So then I think then we can move on to the next speaker. But before.